Так, добрый день. Начнем лекцию. An interesting modification of Forney codes was suggested by Eustacson. In that modification, instead of the code on Warshamov Gilbert bound, which is found just by an exhaustive search, we use Wozencraft code. So the resulting code is called Forney Eustacson Wozencraft code. Let me remind you what are Forney codes. Forney codes are obtained if we consider concatenation of codes where the outer code is Reed-Solomon and over the alphabet, which has 2 to the k letters, so some 2 to the k m 2 to the k minus m plus 1 code over the 2 to the k letter alphabet. And this is Reed-Solomon. And as inner code, we use some code where the code length is, say, the block length, the alphabet is 2, the dimension is k, so that we can identify messages of the inner code and letters of the outer code. And here we use some n, block length n, and here we use some the maximal possible distance with parameters n and k, and this inner code is found just by an exhaustive search. This is an inner code, and the result we obtain 2 to the k times n code with code length 2 to the k times n and binary alphabet. And this was the reminder what are Forney codes. But now the modification suggested by Eustacson is the following one. Instead of this code as inner code, we will use Wozencraft code. So now, oh, sorry, I shouldn't erase this one. So instead of this one, we use an inner code, which is Wozencraft code. Wozencraft code has rate 2, so now the block length is 2 to the 2 times k, the dimension is k, and the distance depends on which alpha we use. Recall that the inner code, which is now Wozencraft, encodes a k letter message, which consists of just k bits. By that message concatenated with alpha times x, where alpha is some parameter. Alpha is chosen from the field of cardinality 2 to the k, and to being able to multiply alpha by x, we consider x also as an element of this field, fixing some linear one-to-one correspondence between k letter strings and elements of that field. And the relative distance of this Wozencraft code depends on alpha. And we know that for majority of alphas, the distance is close to the distance of the maximum of the code used in Forney's construction. But this is not all. Instead of searching for the best alpha, for which the distance is a maximal one, we will use different alphas. More precisely, we use for each block its own alpha, and more precisely, alpha will be just equal to the number of the block. So the code words will look as follows. So the code words of the outer code are sequences of values. So the messages are polynomials of degree at less than m. So this is the outer code, the Reed-Solomon code. So the messages are polynomials, and the code words are values of those polynomials in all different elements of the field, of 2 to the k element of this field. And now we use as alpha xi to x1 to encode this guy, x2 to encode this guy, and so on. So this code word is encoded. Each block of this code word is encoding using the some Wozencraft code, and instead of k binary symbols, k bits, we obtain 2 times k bits, and the encoding is the following. So according to the encoding of Wozencraft code, we map p of x1 to p of x1, comma p of x1 times x1, and so on. Instead of this code word, we obtain that code word, this one, p of x 2 to the k, x 2 to the k. In other words, this code word may be described without any reference to the initial outer Reed-Solomon code. So you see that for the resulting code, the messages are also polynomials of degree less than m, where each coefficient is considered as a k-letter binary sequence. And the message and the code words are the values, the table of values of that polynomial in all points, and also of the polynomial p of x times x. So in brief, for Forney, Eustace, and Wozencraft code, we map a message p to the code word, which is the table of p and plus the table of x p of x, the table of values of p of x, and concatenated with the table of values of polynomial x times p of x. So the message has mk bits because this is polynomial of degree less than m. So it has m coefficients, each of k bits. So we obtain the code where the messages have mk bits. And two tables in total have 2 to the k times 2k bits. Because there are, each table has size k times 2 to the k. Because the number of values of the polynomial is 2 to the k, we evaluate it in all 2 to the k points, and each such value is encoded by k bits, and 2 is because we have two tables. So as a result, we obtain 2 to the k times 2k block length, m times k dimension, and their distance can be calculated, but it's not an easy task, because to calculate the distance, we need to understand what's the distance for each of these alphas. And we should add 2 to the k minus m plus 1, so to say, worst distances of Wozencraft codes, because in the worst case, all the errors in Reed-Solomon, all the wrong blocks will correspond to those alpha for which the distance of the Wozencraft code is the least. But this is not bad, because we know that for the majority of alpha, that distance is large enough, close to that the distance of the codes of on the Warshamov-Gilbert curve. And so we obtain almost the same distance as for Fournier code. Okay, because this distance is hard to calculate, so I keep here an asterisk. And that's all I can say about this idea of Eustason. Так, скажите, есть вопросы по поводу? Any questions about Fournier, Eustason, Wozencraft?
So
Yes.
outer code isn't actually Reed-Solomon.
It is. It is. Yeah, the outer code is Reed-Solomon code.
But in Reed-Solomon code, aren't x1, x2, and etc. fixed?
Yes, in Reed-Solomon code, we can choose any pairwise different value elements of the field. But if the block length is equal to the cardinality of the alphabet, we have actually no choice. We have to choose all elements of the field in the table. And so the only thing we can change here is the order in which we arrange those 2 to the k different elements of our field. So our field has exactly 2 to the k elements, and all xi's belongs to this, and they are pairwise different. And so the only thing we can change is the order, but the order is not important. We do not care which order to choose here.
Okay, thank you.
Okay, now we will proceed to the so-called Plotkin bounds. Plotkin bounds are new necessary conditions for existing distance of the code. and they answer the following question. So let's recall, for example, for the binary alphabet, which necessary and sufficient conditions we have so far. So assume that Q is 2. Then we have two curves. Here is D over N. Here, this axis is K over N. This is 1, and this is the yes area where we know that there is a code. So, sorry, this is no area for which there is no code. And this is the yes area, this one, for which we know that there is a code. So let's paint it in blue, in green, this one, and let's paint it in red, this one. No area, no code here. There is a code here. So this is the Hamming bound. This is the Varchamov-Gilbert bound, and you see that there is a large area in between these curves, and the difference between these curves becomes huge for small rates where K over N is close to 0. You see that we have many relative distance for which we have no answer. Is there a code or there is no code? For example, this bound, for example, the following question is not answered by these two conditions. Is there a code for which D over N is equal to 1, or there is no such code? Or is there a code for which D over N is equal to something close to 1, for example, to 0.9? For which rate there is such code? And it's easy to understand that actually both these questions are answered in negative. Because what does it mean, for example, that the relative distance is exactly n? This means that code words differ in all n positions. But it is to understand that there are only two strings possible that differ in all n positions. So because the second code word must be obtained by flipping all the bits in the first code word. So for D over N equal to 1, we know that the number of code words is at most 2. So that means that the rate of the code is negligible. The dimension is 1, and the rate is then negligible. And actually, even if the distance is 0.9 times n, then the number of code words is also at most 2, because the following simple arguments may be used. So fix one code word, and if we have two other code words, then they must differ from this one in 90% of positions. So for example, this C2 is different from this in all these positions, and C3 is different from C1 in another 90% position, for example, in those. But from this picture, we see that C2 and C1 should coincide in all these positions which are in between, and there are 0.8 such positions. So this simple argument shows that C1, the Hamming distance between C1 and C2 and C3 can't be 0.9 times n. It is at most 1/5. And so even this is impossible. And actually, one can prove that for binary code, even the distance slightly larger than 1/2 is impossible. So Plotkin bound actually proves that the red area can be increased. Let's write it like that. To all these things. So all these question marks are actually in the red area. So, and this is Plotkin bound for the binary alphabet. Okay, now I will state a Plotkin bound more accurately. And before this, I will present some geometrical theorems which we need to prove Plotkin bounds. So this is a very interesting part of my course. We will see that some purely geometrical theorem imply very important consequences in the coding theorem. And the geometrical theorem I mean are of the following form. Assume that we want to find vectors, for example, in one-dimensional or two-dimensional or n-dimensional space, the unit length vectors that form pairwise obtuse angles. So xy, the length of each xy is 1, and xi, xj is, say, less than 0 or less than or equal to 0 for all distinct I and j. And the question is how many vectors we can choose. For example, in one dimension, we can choose two such vectors, +1 and -1. So for dimension n1, there are at most two such vectors. For the plane, we can choose three such vectors. If we want that the inner product is non-positive, and even for if we allow also right angles. So that means that n is 4 if we allow non-strict inequality here, and n is 3 if we require strict inequalities here, 2 or 3. And geometrical lemmas we need find the maximal possible n in that case. And it turns out that if here we require non-strict inequality, then the maximal possible n, the maximal possible number of vectors is 2 times n. And if we require strict inequalities, then one can guess that it is n+1, as we had here. So for non-strict, we had here 2 and 2. For strict, we had here 2, 3, and so on. So the maximal possible number of such vectors is n+1. And also, we are interested in how large can be this negative number, assuming that it is strictly negative. And the geometrical theorem answer both questions, and now I will state them. So first, we will state the necessary and then the sufficient condition. So first we will handle the strictly negative case. Assume that we have capital N vectors of unit length from n-dimensional Euclidean space and also assume that we know that xi, xj, the inner product, are strictly negative, and they are at most some negative number minus epsilon. Then the theorem claims that, first of all, the dimension should be larger than n-1. In other words, the number of vectors should be at most the dimension plus 1, and epsilon can't be very large. Epsilon is at most 1 over n-1. It is easy to memorize. Everywhere we have n-1. So in the lower bound for the dimension, we have just n-1. In the upper bound for epsilon, we have inverse of n-1. So this is the sufficient, the necessary condition. And the second sufficient condition shows that in the first item, everything is tied. So it claims the second item that for all capital N larger than 1, there are such vectors for which both bounds are attained. So there are capital N vectors in R to the n-1, capital N-1, each of unit length, and such that the pairwise inner product are exactly -1 over n-1. So they can't be less than these because of the first item, and so they are exactly as claimed as this lower bound, upper bound for epsilon. This purely geometrical theorem will apply actually the Plotkin bound, as I said, for the binary alphabet and also for arbitrary alphabet. I forgot to say that for arbitrary alphabet, we will the Plotkin bound will state the same thing, but instead of 1/2, we will have here a 1 minus q in general case. So in general case, the Plotkin bound states that there is no code with relative distance equal to 1 minus 1 over k in the case of q letter alpha. Okay, let's prove this geometrical statement. The bound on epsilon is very easy to prove. So let's prove first the bound for epsilon, this one. So y epsilon is at most 1 over n-1. To this end, we consider the sum of all vectors x1 plus xn and its inner square. So we multiply it with itself. First of all, we know that this is non-negative because this is the square of a vector. On the other hand, we can represent this inner product using linearity of inner product as the sum of all xi, xj, the product of xi and the xj over all pairs of I and j. And this sum may be rewritten as follows. First of all, let's distinguish all the terms where I equal to j. There are n such terms, and each such term is exactly 1, because our vectors have unit length. So we obtain n ones in our sum. And the remaining terms are the sum of xi, xj, where I is different from j. There are n squared minus n such terms, and for each term we know that it is at most minus epsilon. So we can upper bound this by n plus n times n minus 1 times minus epsilon. And so we know that this sum is non-negative. So we know that this sum is larger than or equal to 0. In other words, we know that epsilon times n minus 1 is less than 1. And this is exactly what we need to show. So this means that epsilon is at most 1 over n minus 1. So to prove this inequality, we just need to consider the inner square of the sum of all vectors and use this assumption. Now, let's prove this bound. And to prove this bound, first of all, note that it doesn't depend on epsilon. So to prove the lower bound for the dimension, we just need to know that all these inner products are strictly negative. So we know that inner products of different vectors is strictly negative, and want to show that the number of vectors is at most n plus 1. Oh, let me see somehow what the proof of this. So this is easy. This is because because of the following thing: choose some n-1 vectors among our vectors. For example, the first n-1. And we claim that they are linearly independent. And since they are linearly independent, the dimension should be at least the number of such vectors. So assume the contrary, that some non-trivial combination of those vectors is 0. First of all, we need to show that in this combination, non-trivial combination, there should be lambdas of different sign. So assume this, and also assume that lambda 1, lambda n-1 are of the same sign. For example, they are also non-negative or non-positive. In that case, we multiply this equality by x n. So we have one more vector, xn. Let's just multiply by xn. On one hand, we have 0 because we multiply a 0 vector by xn. On the other hand, we can use the linearity of inner product and express this as a sum of lambda I x I times xn. And here we know that all these guys are negative, and all lambda have the same sign. And so at least one of those lambdas is non-zero. And hence, in the right-hand side, we have a sum of expressions of the same sign, and at least one of them is non-zero. And so such a sum can't be 0, and we have a contradiction. So we have assumed that this linear combination is 0, and also assumed that they have the same sign. Hence, we may conclude that at least two of them have different signs. So there are lambda I, lambda j of different signs. So some lambda I is positive, and some lambda j is negative. And in that case, we will also obtain a contradiction, but this time the contradiction is obtained as follows. We move all the negative, all terms with negative lambda i's in the right-hand side of this equality. So we obtain that the sum of some lambda I xi is equal to the sum of some, call them mu j xj, where all lambda i's are positive and all mu j's are also positive. And all the sums are non-trivial. That means that at least one term is in the left-hand side and at least one term is in the right-hand side. And in that case, we obtain a contradiction just by considering the square of these vectors. So this is the same vector represented in two different ways. So its inner product, its inner square is non-negative. Because it's a square. And on the other hand, using linearity, we can express it as a sum of all ij, lambda I mu j, xi times xj. And now we obtain a contradiction as follows. We know that xi xj for all ij is strictly negative, this one. And this product is positive or zero, but at least one such product is positive because we know that both sums are non-trivial. There is at least one positive lambda I and at least one positive mu j. And so we obtain the sum of terms of the same sign, and at least one of them is strictly negative. So we can't then have a sum which is greater than or equal to zero. So a contradiction also in this case. So we have proven half-wire theorem to the first item. Так, есть вопросы? Are there any questions about the proof of the first item of the theorem? Так, ну хорошо, тогда давайте перерыв на 5 минут. Break for 5 minutes. Okay, now we need to prove the second item, where we need to construct for all n, starting with 2, x1, xn, attaining both bounds. And for example, for n is 1, for n equal to 1, we know that we can x1 take plus 1, x2 to take x2 minus 1, and we will obtain just x1, x2 equal to minus 1, which is our case 1 over n minus 1. For n, and these are one-dimensional vectors. For n2, we take 3 unit vectors, which form the angles of 120 degrees. And in that case, the inner product is a cosine of 120 degrees, which is exactly minus 1/2 as required. Sorry, this is for n equal to 2, this is for n equal to 3. And now we need to repeat this, I mean, to prove this for larger n. And the easiest way is to do this is just by induction. So we can start induction from n equal to 2 or from 3, doesn't matter. How to make the step, induction step from n to n plus 1. So we are given n vectors in dimension n minus 1. So they live is in R to n minus 1, capital N minus 1. We are allowed to increase the dimension by 1. That means to add to those vectors 1 new coordinate, and also to add 1 new vector. And this is done as follows: a new vector, the added coordinate will be equal to 1 over n. So we just add as new coordinate 1 over n to all those vectors and denote those vectors by x tilde xi. If we do that, then of course we will increase the length, and so to keep the length of vectors equal to 1, we multiply them by some fixed constant alpha. And alpha is chosen so that the length of this vector is again 1. And it is easy to understand what alpha we need to choose. If we take the length, the square of this vector, we will obtain alpha squared plus 1n squared. And so if we want this to be equal to 1, we need to choose alpha being equal to square root of 1 minus 1 over n squared. So let's fix this alpha, and then transforming given xi's in that way, that is multiplying them by this constant alpha and adding 1 over n as new coordinate, we will obtain other new n vectors which now live in R to the n. And as a new vector, we consider the vector which has 0 in all the previous coordinates and minus 1 in the new coordinate. This will be tilde x n plus 1. And that finishes the construction, and the only thing you need to verify that the inner product as required. So the inner product of the new vector and any of the previous vectors, I mean any of the tilde vectors, is exactly -1 over n, because we multiply -1 by the last coordinate and we obtain -1 over n. So xn times tilde xi is equal to -1 over n as required. Now we need to verify the same for the product of xi tilde xj for I and j at most 10. And this is also easy to verify, because if we multiply this by this is the same as multiplying alpha xi by alpha xj and adding 1 to this, the product of new coordinates, that is 1 over n squared. And this is equal to alpha squared, because alpha squared times the inner product of xi xj. And we know what this inner product is, because by induction hypothesis, this inner product is equal to -1 over n minus 1. So we obtain alpha squared is 1 minus 1 over n squared, and we multiply it by -1 over n minus 1 plus 1 over n squared. Now we see that everything is okay, because n squared minus 1 over n squared can be represented in n minus 1 times n plus 1. And we divide it by n minus 1, because we have here n minus 1 in the denominator. So they cross out, and we obtain n plus 1 with the negative n plus 1 over n squared. And so we obtain minus n plus 1 over n squared plus 1 over n squared, so which exactly equals minus n over n squared. In other words, -1 over n. So we obtain the same value as before. So we see that the new vectors satisfy all the requirements. So they live in n-dimensional space, because we had n minus dimension n minus 1, added 1 new coordinate, and the pairwise inner products are the required -1 over n. And so the theorem is proved. Any questions about the proof? Так, скажите, вы видите сейчас доску?
Да.
Нет, сейчас не доску, а ваш диск.
Ага, это плохо. Так, сейчас. Так, верну доску. Так, ну-ка, я понимаю, вопросов нет про доказательства. Now we need to state and to prove the second geometrical theorem needed for the second Plotkin bound. So the second geometrical theorem, theorem 2, It is the case where their inner product are just non-positive. That means that we have several vectors, non-zero vectors, which form pairwise obtuse angles or 90 degree. So that means that the inner product is non-positive. And we want to find out how many such vectors are in n-dimensional case. And the theorem states that the maximal possible number of vectors is 2 times the dimension. So assume that x1, xn are in n-dimensional Euclidean space. They are non-zero. Or without loss of generality, we may assume again that they have unit length. And xi, xj is at most 0 for different xi and j. Then from all of this, we claim that the number of vectors is at most 2n. And here it is very easy to understand that this upper bound can be attained. For example, to attain this bound, we consider the vectors which are coordinate vectors, x1, x2, x3, say for 3. So they are pairwise orthogonal, and there are n of them. And also we take minus negative vectors, minus x1, minus x2, minus x3. And now we have 2 times n vectors, and the inner product are either 0 or minus 1, which is okay. So either they are orthogonal or one of them is minus another one, and so the inner product is minus 1. So this picture shows that actually this bound can be attained. And so we do not even state it because it's not interesting, because as this is trivial. So we need just to prove this one. And the proof is the following one. First of all, we consider the maximal linear independent subsystem of this system. Maximal linear independent subset of this. No, without loss of generality, we can assume that these are the first, say, m vectors. This subsystem is equal to this. Is the largest, this subset is that subset. Then each of remaining vector can be expressed through these vectors. And we need actually, our claim is that n is at most 2 times this n. No, and hence is at most 2n, because all those vectors are in n-dimensional Euclidean space, and hence there is no then the maximal system has independent system has at most n vectors. So we will prove this inequality now. And this will follow from this will be done in 2 steps. So in step one, we will show that if we express some vector xk where k is larger than m, as a linear combination of those vectors which are linearly independent, then all those coefficients are non-positive. So when we express some xk as a linear combination of our bases, then all the coefficients in that linear combinations are non-positive. So this is our claim. So why is this? Assume the contrary. That is that there is a positive coefficient. Then we will do the same trick as before. We will move all all terms for where lambda I is negative to the left-hand side. So we will obtain some sum of mu j xj equal to some sum of lambda I xj. And here, so all lambda i's here are positive, and also all mu j's are also positive. And here we have at least one term. And now we make the same trick. We multiply the left-hand side by the right-hand side. And the right-hand side is non-zero because we have here at least one term, and this is a linear combination of our vectors from our system. Sorry, I should write here xi. And they are linearly independent. So any such non-trivial combination is non-zero. So when we take the product of the left-hand side and the right-hand side, we obtain strictly positive value because this is the inner square of a non-zero vector. And now we again use linearity. We obtain the sum of mu j lambda I xj xi. And we see that in this expression, all the signs are the same because we know that xi times xj is non-positive, and this product is positive. So we obtain the sum of non-positive values, which is, of course, non-positive then. And so we obtain a contradiction that 0 is larger than 0. And so on step one, we have shown that in such a expression of xk through this, all the coefficients must be non-negative. Okay, Now on step 2, we want to prove that the remaining vectors are linearly independent. So the remaining vectors are x m plus 1, those which are not in our basis. So we want to prove that they are linearly independent. And why it's enough? It's because all of them can be expressed through our basis of, through our system of m vectors, and hence the number of these vectors is at most n. So on step 2, we prove this. Again, assume the contrary. That the sum of some linear combination of these vectors is 0, non-trivial one. Non-trivial combination. Now, by step 1, we actually can conclude that in this sum, lambda i's should have at least 2 different signs. I mean, it's impossible that all of them have the same sign. And that's because we can express all those xi's through our basis, and in all the coordinates of this vector in that basis have the same sign by step 1, because we know that if some of these vectors is written as linear combination of x1, xm, then all the coefficients are non-positive. And that means that coordinates of all those vectors xk in that basis are non-positive. And so to obtain 0 in every coordinate, we need to have some cancellation. And such cancellation may happen only if some coefficients are positive and some of them are negative. And here we use that all our vectors are non-zero. So we know that there are strictly negative coordinates. And to cancel such a coordinate with some other number, we need lambda of different signs. So we conclude then there is I such that lambda I is positive, and there is J such that some lambda J is negative. And so again, we can use the same trick. So we have some combination of our vectors. Here, I ranges, I is greater than k. So some combination, which is equal to some other combination, where j is also larger than k. And both of them are non-trivial. Non-trivial combinations. And also we know that this is non-zero, because we just have proved that a non-trivial combination where all coefficients have the same sign can't be zero of our vectors. And again, we take the multiply the left-hand side by the right-hand side. So we obtain on one hand a positive value because this is an inner product of non-zero vector. And on the other hand, if we use linearity, we obtain the sum of lambda I mu j times xi xj. And again, in the right-hand side, everything is, all the terms have the same sign, and this sign is negative, or zero, because lambda I is positive, mu j is positive, and the inner product is non-positive. So we obtain again a contradiction that 0 is less than 0. So we have shown that the remaining vectors are linear independent, and hence their number is at most m. And so the total number of our vectors is at most 2m. And we are finished. Вот вроде бы я доказал вторую теорему. The second theorem is proved. Are there any questions? Okay, now I can state and also prove both Plotkin bounds. So Plotkin bounds. Let's start in the simplest case for first for binary alphabet. For k equals to 3. If we have certain code words with the following property that the distance, Hamming distance between different is at least beta n, where beta is more than 1/2, then the number n, or assume that we have C1, Cn code words over the binary alphabet. We have a certain number of code words of length n, such that the minimal distance of the code is at least beta n, where beta is strictly less than 1/2. Then the bound claims that n, the number of code words, is bounded by some function of only beta. And that function is 1 over 2 beta minus 1 plus 1. And this is the first Plotkin bound. And the second Plotkin bound states that if pairwise Hamming distance is at least n over 2, so it claims something when for beta exactly equal to 1/2. Then the number of code words is at most 2 times n. So in both cases, the number of vectors is negligible, because in the first case it's bounded by some constant dependent on only beta. In the second case, it's bounded by a linear function of n, which means that the rate of our code is very small. So the dimension is logarithmic in n, and the rate is something like, the rate is at most log 2n over n, so very close to 0. And for arbitrary Q, the first Plotkin bound says that if the distance, Hamming distance between different chord words, at least beta n, where beta is larger than 1 over q. So instead of 1/2, in the general case, we have 1 minus 1 over q. When q is 2, it is 1/2. Otherwise, it is larger. Then n is at most 1 over q minus 1 times beta minus 1. This is in the denominator and plus 1. So for the binary alphabet, q over q minus 1 is 2, and we obtain exactly 2 beta minus 1. In general case, instead of 2, we have q over q minus 1. And the second Plotkin bound says that if the pairwise distances are at least this beta 1 minus 1 over q times n, then the number of chord words is at most 2 times q minus 1 times n. So when q is 2, this is exactly 2n as claimed. In general case, instead of 1 here, we need to put q minus 1. And so you see that for q equal to 2, we have just a special case of that theorem. I have no time prove the Plotkin bounds in general case, but for binary alphabet, I have some time, and I will explain. This is a very easy thing. Let's prove it for binary alphabet. And for binary alphabet, also in general case, we will use for the first Plotkin bound, the first geometrical theorem, for the second Plotkin bound, the second theorem. And both are proved by the same trick. We replace each chord word by a vector which is in R to the n. So each ci is replaced by some xi, living in 2 to the n, R to the n. And replacement is the following one. We take all the bits of ci, we replace, say, 0 by minus 1 and 1 by 1, and we divide the remaining vector by square root of n to obtain a vector of unit length. So the replacement is as following. For example, 1 is replaced by minus 1 over square root of n, 1 minus square root of n, 1 minus square root of n, and so on. So each letter is replaced either by plus 1 square root of over square root of n, or by minus 1 over square root of n, dependent on whether it is 0 or 1. So we obtain some vector in R to the n. And the inner product, first of all, it is easy to see that the length of such this vector is exactly 1. We have divided by square root of n to obtain a vector of length 1. And second, it is easy to see that the inner product of any such vectors is expressed to the Hamming distance between them, through Hamming distance between them. Because when we multiply two such vectors, then different positions, different bits of chord words correspond to the product of plus 1 over square root of n and minus 1 over square root of n. And they contribute minus 1 over n in the inner product. And if the bits are the same, they they contribute 1 over n. So that means that the inner product of xi, xj is exactly equal to n minus the Hamming distance between the coordinates ci and cj, and minus, so this is the number of symbols where they coincide, which each of them contributes 1 over n. And the Hamming distance, we subtract again the Hamming distance, because this is the number of positions which contribute minus 1 over n. In other words, we obtain 1 minus 2 times the Hamming distance over n. And so to prove the first Plotkin bound, we just upper bound the Hamming distance, the inner product, by we know that this relative distance is at least beta n. So we can state that this is at most 1 minus 2 beta. And to use the first geometrical theorem, first of all, we mentioned that because beta is larger than 1/2, this is strictly negative, and call this our minus epsilon. So, and this is strictly negative. And by the first geometrical theorem, theorem 1, we know that this epsilon is at most 1 over the number of vectors. In other words, n minus 1 is at most 1 over epsilon, which is 1 over 2 beta minus 1. And this is exactly what claims the first bound, that the number of coordinates is at most 1 over 2 beta minus 1 plus 1. And to prove the second bound, we just mentioned that we know that this relative distance is at least 1/2. So that means that xi, xj is at most 1 minus 2 times 1/2. That is at most 0. And again, by the second geometrical theorem, we know that the number of such vectors is at most 2 times the dimension. What claims the second Plotkin bound? Так, ну хорошо, все. Сейчас я вам дам этот тест. Так что это вот это, что ли? Да. Так, сейчас я надеюсь, что у вас нет возможности редактировать. Так, видите тест?
Да, да, видим.
Так, значит, конец у нас будет, там 3 задания всего, ну, 10 минут, 14-10. Так, ну уже пора сдавать. Значит, давайте обратный отчет начну. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Так, все. Так, ладно, до свидания. Всего хорошего.
До свидания.